Well, hello everyone. Session 19 today. We're going to do two things. We're going to finish up the torsion stiffness in monocoque vehicles, and then we're going to talk just a little bit about torsion in non-monocoque vehicles. So these are basically bodies with frame. Okay. So first we're going to clean up with the monocoque structures. Just to remind you where we ended up with, we had a nice calculation equation that was based on the work-energy balance for the torsional stiffness, and that was a function of the G times T, the shear rigidity of each of the sides of the car, each of the shear-resistant members. And the way that we determined that value of shear rigidity, we imagine it being put into our little test fixture here, apply a force, measure deflection, and then use this relationship to calculate that effective rigidity and shear. And then we could calculate the torsional stiffness of the body. So where we ended up, we were just going to start to talk about the side frame and how do we go through this procedure for it. So here now we're looking at the side frame, the same set of beams that we looked at for bending, but now we're going to be loading them in a very different way. So if we could imagine looking at one side of the car here, applying a downward load in the front and upward in the back, and then on the other side of the car, this would be symmetrically opposite. We're applying these loads at the suspension attachment points, and that would transmit this kind of a shearing effect to the side frame. So it would want to deform something like this in the lower picture. And we're going to imagine taking the side frame out of the car. It's one of the shear resistant kind of panels in the car. And we want to figure out what is its effective G times T, shear rigidity. So the way we can do that, of course, is to imagine it being put into this fixture, and with the load and deflection being measured, and then using this equation to come up with the GT effective, and then from that we can use it to calculate torsional rigidity of the body structure. So here is an illustration of how we're going to actually do this using the little finite element model that we used before for bending. So we're not going to actually put the picture frame on here. We're just going to hold the side frame at the front and the back of the rocker. So that's the equivalent of these. And then we're going to apply a load across the top. That's the equivalent of this. And by doing this, this will effectively put it in the state of loading that we would be in this test fixture up above. Okay. So we apply a load, we measure the deformation, and then we use this equation in order to calculate GT effective. And if you remember, the length of the applied load is the L value. So this is the A, this is the B. So here we've substituted those in for the kind of overall length of the side frame and the overall height of the side frame. Okay, so let's see how we actually implement this. So here is the model that we had used before in class for the intermediate size car. We need to know a couple other things. One is the track of the vehicle, and the other is, well, what are we shooting for? The torsional stiffness requirement. So from this and knowing the section sizes, so this is our preliminary guess at the various sections. We're going to do an analysis using the little program in Excel. So if you remember, this is the page where we entered the values here. So here we've entered the values for all the beams, and in this case we're gonna add in the joint rates. Okay, so we have a joint in these locations here, but rigid at the bottom. Okay, and this is just arbitrary. In a real world analysis, we'd want to have joint rates all the way around. So here's the situation that we're We're going to model. Again, we're kind of pretending that this little fixture is there. We're actually going to just let the side frame provide those constraints. The applied load will be at the top of the B pillar here. Okay. So for our particular model, the A dimension is 1600, the B dimension is 1100. We're just going to arbitrarily apply 1,000 newtons. This is a linear elastic problem, by the way, so we're going to be applying a load, measuring a deflection. So if we apply 1,000 here, we'll get some answer for delta. If we would have applied, say, half of that, would get a different answer, but it's all linear. So when we take the ratio of the applied load to the deflection, it's really arbitrary what load we apply, as long as we're linear and elastic. Okay? So this is 1,000 is just a convenient value to use. Okay, so again, this is our little beam solver in the Excel model, and it's you know where it's found on Canvas. We're going to be using the same tab here. We want side frame, deformation, and stress. So everything will be identical to before. The only difference here is we're going to be applying different restraints and different loads. Okay, so for the bending load case, if you remember, the restraints were at the suspension attachment points at point 10 and 11. So our little car model looked like this. We had restraints like this and this, and the load was at number 9, which was beam number 9 is right here, and we're applying at the end. So this is what we had before for using this. Now we're going to do something a little bit different. Here we're going to be applying the restraints at 1 and 7. So here these go away. So this will be at 1 and 7. So these are like the bottom of our picture frame setup. And then the test load will now be at beam number 4 at its starting point. So this goes away, and we're at beam number 4 right at the starting point. And the direction has changed. We're now in the X direction. And again, just for convenience in this case, a stiffness case, we're going to apply a load of 1,000. Okay. So other than that, your old hands at running this model, here is the results. So you see a very different kind of a load case here. So here and here, we see the suspension attachment points are moving, but we don't really care about those. We've applied our load here of 1,000 newtons, and now we're interested in, again, the deflection at that point. So it's the deflection of node number 4, and now it's in the X direction, kind of the horizontal direction. And we see that value is 4.23, so that goes in to our equation here. The applied load is 1,000. The A dimension, that's this dimension here, and then the B dimension is the height of the side frame. Okay. So we run all this through, and now we get an effective shear rigidity of the side frame of 162.5. Okay? So if you can kind of imagine, if we had a flat panel that was non-buckling, we could put that into our model to get the result for the overall torsional stiffness of the body. Okay, so that's how we'll use this. So we take this now to our little equation, and again, just for convenience, now what we're going to do here is say that, well, now we know we have a flexible side frame, and it's going to be much more flexible than the perfectly flat rigid panels that we had before. So this quantity, which is 1 over K, remember, this is really big for all the other panels, so that this quantity goes to 0. Okay, so just for convenience, we're just going to ignore these and say that since these are all very rigid panels, they're relative to the side frames. We can say that this quantity is equal to 0. And then all we have to do is plug in for the side frame values. Okay, so here's a simplified formula. And now this value of GT effective is what we had just calculated and what we want to apply into this equation. Okay, so here is that value. And then here's, again, the A and the B values, this kind of the size of the side frame. And we just kind of crank this thing through 5 times 10 to the 8th Newton millimeters per radian, and then when we put in the traditional units, Newton meters per degree, we get 8,774 Newton meters per degree. So that's just due to the side frames going into the shear deformation that we looked at before. So this is how we can really use our little model that was specifically designed for kind of flat shear resisting panels, and use this idea of this little pinned picture frame model to get an effective GT and then plug it into this equation. Okay, so now we have a pretty good calculation method to come up with torsional stiffness of the body structure. So one thing I just want to note here is this is pretty low. We said before that our requirement was about 12,000 Newton meters per degree. So we need to improve things. So how would we do it if we wanted to concentrate on the side frame? Well, going back to the model, we'd use the same kind of a general methodology that we talked about there. We would use the bending energy in order to help direct us to what would be the most valuable to improve. So here it's saying that the B pillar lower as a structure and as a beam would be important to change, and then the B to roof joint. So that would be this joint up here. So we could go in and change those, kind of see where we go with this. We'll have less deformation. That will increase the GT effective, and then we could come back and plug it into this relationship and calculate the new torsional resistance. Okay? So I think in the homework assignment you got a chance to try this out. Let's talk a little bit now about some of the other panels in the car. What we're going to look at is the backlight and the windshield area, the roof, and then we're going to look at the seat pack. So these are all kind of relevant structures. Generally, the floor and the dash panel are very rigid members, so we don't have to worry about those too much. Okay. So the first one we're going to look at is the windshield and backlight, and generally this is a very rigid member. So we're looking at it not because it's kind of a problem area. We're looking at it because it's something kind of unexpected, that this is actually is a structural member in the car. So we need to look at really the windshield adhesive system. So we have, if we look at this little corner here, cut. So here's the roof. Here's the flange that the window attaches to. Here's the windshield itself. And then most vehicles, that windshield is held in place by a little bead of urethane adhesive. And these dimensions, just very roughly, this might be 4 millimeters, and this might be the same here. Just to give you a feel for the size. There's another method that the windshield is retained, and that's via a rubber gasket. This is usually on smaller pickup trucks. You'll see something like this where that's the gasket. This is very flexible and shear, so that for these kinds of vehicles, the windshield really is not a structural member because of all the flex that you get in this member. So this is the configuration that we're going to be looking at. And just to give you a feel for what is the mechanism that gives this some rigidity and shear, let's take a look at the glass here. We're looking at the front of the car here in this picture here. And the glass is shown in gray. And the glass just doesn't deflect much relative to the to the ring of steel around it. If it did, it would crack. So we're going to take a section right here, and let's see. This is the body opening. So this is the steel flange. If we have a steel vehicle, steel flange that goes around the windshield opening. Okay, and if we twist the car, that flange will distort into that diamond-shaped pattern that we talked about before. And now we're going to cut another section and look at that in this direction here. So here's the body in white structure. This is like the A-pillar that we're looking at. Here's the flange. So here's the unloaded condition that we're looking at. The windshield and then the adhesive with some shear modulus associated with it. And as we twist the structure, you see that there's some deformation here. The glass kind of stays in place; it doesn't move, but we get some distortion of the flange, the A-pillar flange. Okay, so here's the undistorted windshield. Here's the shear flange moving from the DAS position to the solid position. So what that's doing is it's shearing this little piece of adhesive. And this is really where we get all the rigidity from. Okay, we have a rigid glass, and then this little adhesive is flexing, and that's where we get the G times T in this case. Okay, so our little model looks something like this, where we're replacing with 3 springs now something that we had only one spring in before. Right? This was the G times T effective for the system of windshield and adhesive. Okay? So here we now have 1 spring that's for the windshield frame by itself. So if we just took the window out and twisted the car, we would have some rigidity of that metal ring would still have some resistance to distortion. And then on the other side, we have the windshield in series with the adhesive. Okay, so this is kind of the model. And various cars have different combinations of these 3 springs, so that it gives it slightly different behavior. So let's just take a look at the relative shear rigidity for each of these systems. So here we have the G times T effective for the windshield frame, for the adhesive ring by itself, and then for the glass by itself. Okay? And these units are in the English system, but what we're looking at is just the relative rigidity for each of these. Okay? So if you can imagine putting just the windshield frame into our little pin system, we would measure some shear rigidity given by this value. If we had kind of a plate on the top of the adhesive bead and then one on the bottom, and then we kind of shear those 2 plates, this is the value that we would get for the shear rigidity of that. And then for the windshield itself, it's actually quite rigid. It has the property somewhat similar to aluminum from a stiffness standpoint. So you see the glass is very rigid, the windshield frame is very flexible, and then the adhesive is somewhere in between. Okay. So in this case, for this side, for most cars, this is very flexible. The windshield we see is very rigid, so this is going to act almost like a solid bar, and then therefore this adhesive surprisingly dominates the behavior. So this is what the system actually acts like. It's really the G times T of the adhesive that's really dominating the behavior. Okay? And this is kind of a typical value of about 10,000 newtons millimeters for that GT effective of the adhesive. And you might be saying, well, this is really kind of wild. I don't believe it. So here's one way to hopefully convince you. What we're plotting here is several vehicles. Each dot represents a a body in white actually. This is the torsional frequency of that body in white with the glass in place. And then along the bottom is the torsional frequency without the glass. Okay? So we're looking at a frequency here. And we know generally that frequencies are equal to the square root of k over m. And this is the torsional stiffness in this case. And this is like the rotary inertia of all the various parts of components that are attached. So what we can kind of visualize this graph is not plotting torsional frequency, but plotting something that's related to the stiffness of the body in white, in this case with glass, and in this case without glass. Okay. So what you see on this chart are several different regions. There's a really wide region of behavior here. Here's some cars, two cars where with or without glass it doesn't make any difference. So for this guy here, we're a little maybe 26 hertz. For with glass, we take the glass out, it's still 26. Here's a region up here where there's quite a huge difference. So this is a little over 50 when we have glass in, and it goes all the way down to 25 when we take the glass out. So the glass is very much a part of the structure of the car. And then in the middle here we kind of have this little cloud with a medium value where we get some improvement with the glass, but it's not a really huge one, not a 2-to-1 change. Okay? So how do we explain this kind of wide behavior? And our little model will help us do that. So for these vehicles, what that's saying is that the windshield frame, the roof header, the A-pillar, and then the cowl bar across the bottom, that forms a very rigid, shear-resistant ring. Okay, so whether we have the windshield and glass or adhesive and windshield in there or not really doesn't make much difference because this is such a dominant spring. Okay, so that kind of explains this behavior. When we're at the top, what that's saying is that this is that ring that I just talked about, A-pillar to roof rail to cowl bar, is very flimsy, probably because it has very poor joints in the corner. It would be the normal case. So that's almost not a shear-resistant member in and of itself. So all of the improvements come from the windshield adhesive system. And for the majority of cars in the middle here, we have the windshield frame has some rigidity, but the windshield adhesive adds a lot more to it. Okay, so this is kind of a typical ratio of with and without glass. It does provide a very significant improvement in the performance. So as another way to try to prove this to you, we made a little simple cardboard car here. So this is a scale model, and we have basically, it's made of shear-resistant members. All the members are actually flat cardboard panels that are glued together. And we have a little windshield that we can put in place and we can take out. So what we'll do, first of all, we'll kind of look at the behavior, and then we'll look at the quantitative data that's down below. And we're using the same test fixture that now you're kind of familiar with. So up in the corner here, you'll be seeing the load deflection curve occur. Right now we have at 3 of the suspension points, we have the car connected to ground, like for simply supported boundary conditions, and we're going to put a load in at the 4th suspension attachment point. So not perfect torsion, but it's largely torsional behavior. So here's the load deflection curve. This is now with the glass, the equivalent of glass in it. So you see a little bit of distortion there at the point of load application. And now we've removed the backlight in the windshield. Okay, you see the slope of the curve is much reduced. And here you can see the shearing behavior. Look at the windshield ring, and you can see it's going into that diamond-shaped pattern. So we're getting lots of deformation. So this is a case where we haven't reduced it to 0, but it's not very shear resistant. I think in a minute we're going to be looking at the backlight area. So here now is the backlight, and you can see that same basic pattern where we're getting that diamond shape. Okay, and here is the load deflection curves, and here we're not trying to quantify it. We're just kind of looking at the slopes of these three lines. So here is now, this has got the windshield in it. These are 3 repetitions, so it just kind of shows you that we have a very repeatable test. So we're looking at this value, and this of course relates to the torsional stiffness. This is proportional to the torque. This is proportional to the angle of twist. Okay? So here we've taken out just the windshield, so you can kind of see this is the reference here, same reference here. Quite a big change there. And then here we've also removed the backlight, but the windshield was installed. So we're trying to show here that this is a function of both the windshield and the backlight. Okay? So I hope that you're convinced that the glass is a structural member. Now we're going to move on to the roof panel, and we just want to look at this kind of as a generic crown panel at this point. So here we're plotting GT effective for the crown panel divided by or normalized to the same size flat panel. And this is now showing the crown height in the panel. And here you can kind of see that when we have 0 crown, we have a flat panel again, so that's this value is 1. But as soon as we get even a small amount of crown, in very kind of a typical crown, we're somewhere down here, we've really lost a lot of the shear rigidity of this panel. It's still a good shear resistant member, but it's lost about down to 20% or so of an ideal panel, just because now we have a crown in it. Okay? So just wanted to make a comment about that. Now we're going to move on to actually an area that can be problematical, and that is the rear closeout panel. So we're going to be looking at this for sedans here, and also for a couple of SUVs or crossover type vehicles. So how do we get shear resistance in that member, given that we want to have things like luggage pass-throughs in it? So here just kind of a benchmarking a few different ways to do that, and all of these are good vehicles for torsional rigidity. Here is a Lexus. You can see the panel outline looks like that to give some pass-throughs here for things like electrical cables. Here's another way to do this. So here's a beam framework. So we have a kind of good joints here. Here another way, we kind of have a panel that's has some bulkheads in it. So you can imagine that each one of these can resist this kind of a shearing, even though it's not a flat, perfectly closed out panel. And here's another one. This was a ultralight steel auto body, an experimental vehicle done by the steel companies, and they kind of go to this idea of using a very, very thin struts, and you can kind of understand how that would be effective in resisting the shearing deformation. If we want to model something like this one and say, well, this is a beam, that's a beam, that's a beam, that's a beam, and they're connected by flexible joints, and most of the deformation is coming in the joints, then we don't have to do the picture frame kind of an analysis. We can use this equation here, that 4 times K of the joints, and we're assuming these are all identical joints, divided by AB will be the effective shear rigidity. Here's yet another one, a Toyota, and here they have an almost closeout panel, but they wanted a pass-through. And what I wanted to highlight on this one was that we actually did some optimization work on this for the beading patterns. So this was identifying the domain for the structure. This was boundary where the opening was given as a constraint, and then the software told us what will be the optimal bead pattern. And again, this is using this idea of strain energy, throwing out the elements that don't have high strain energy. And then we finally ended up with, well, the case that you see in the little picture there. So one thing about the details of things like this pass opening is generally you don't want to have just a raw edge along this. You want to have some kind of a flange. So here was some little testing that was done on shear resistant members with a hole in them. What should be this flange angle? So here's the no hold value out here. Here's the hole, but with no flange. You can see the very poor performance. So that's with a raw edge here. Here's a flange with 90 degrees. Again, not really too good. So that was like this. And here's a flange somewhere between 45 and 60. It doesn't matter really too much, but you get almost all back the rigidity of the panel. And this is actually kind of a famous design. It's used in the aerospace industry. It's called a NACA flange. You can kind of see the shape that right there. Okay, and this also happens to be fairly manufacturable, so that it's actually more manufacturable than, say, a 90-degree flange, because we don't have the stretch tearing that occurs. Okay, so if you need to put a big hole in a panel, try to use a flange angle that's roughly in that regime. Okay. Now, there's a conference every year. It's called the Great Designs in Steel Conference. I would recommend you go to that website. I think the website that will take you to the homepage is this one. And they're basically OEMs that give presentations about their kind of newest vehicles. And right on this site, I think you can download directly without having to sign up for anything. So I'd like to go through just a few of these because you'll see kind of the relationship between this idea of looking at the most flexible of the shear resistant members in the structure, and then how would you increase basically the shear rigidity as we've been considering here. Okay, so this one has to do with the Honda Civic, and basically one of the areas that they were working on is the one that we've just been looking at, this idea of a closed ring in the rear bulkhead. And you can see they've made it's a beam structure, but they have very nice bulkheads in each of the corners to make sure the joints are rigid. Here's one from Ford Lincoln. So we're looking at the same area here. This is the rear closeout. And you can, again, kind of see the beam structure that they've used here in order to, there's a cross member underneath the pan here that you don't see. Okay. So a lot of good advice here. Angled member here for joint rigidity. The package tray itself is lined up with the panel here. All unnecessary holes have been removed. Here's one from General Motors, the Malibu, and you can kind of, I hope you can kind of see immediately the principles that we've talked about in class have been applied in order to improve the performance here in torsion. Here's the same program. These are a little bit hard to see, but we're taking the rear of the vehicle and we're looking through the open trunk here. And you can see in this base case the earlier version, high stress concentrations, distortions in there. So that's kind of an indication that the joint is not very well performing. And here's the improved version of joint improvement. Okay, so this would be the equivalent of the strain energy leading us to wanting to improve that area. Here's one from Volvo. So here we're looking at a crossover type vehicle. So that rear member, the rear side of the box, is this area here. And you can see some of the principles that they talk about: stiff ring structures. So this would be, stiff in this shearing deformation that we're interested in. Another thing that we talked about when we talked about principles of good joint design was to try to have the structure, pretty much lie within a plane, to not have large discontinuities within the members. Here's one again from Ford, and the reason I wanted to show this one was basically just the FEA model showing the distortion and torsion. So we're kind of seeing this this kind of diamond shape that we've been talking about for the shear resistant members. So you see this is pretty good performance. Again, when we think about it from a strain energy standpoint, we see that this is almost the same color all the way around, so it has very uniform performance for a nice efficient structure. Here's the last one I just wanted to mention with respect to Honda. So again, this is like a crossover vehicle. So we have essentially just a big hole there. And they have a very interesting closed loop construction. So we kind of have one ring going around here, and then another ring going around here. Okay, so lots of different general approaches to this, but I think the idea, hopefully, is you have some intuition that what we're trying to do is make a very rigid ring structure that resists this shearing deformation. So one last area that I want to talk about is, you might notice that when we made our models, we didn't have doors in them. So I just want to make a comment here about the effect of doors on body torsional stiffness. So let's imagine that we took our side frame that we looked at before without a door, but now put a door in it. So here we're going to say that the door structure is very rigid. We're going to simulate it by just this little triangular structure here. We're going to say that it's very well attached at the hinge pillars, and then we're going to apply our load Q here and see what happens. And here's basically what we would see. So the door at the latch will have lots of deformation, and with conventional latches, this deformation happens. It's very hard to get a door that closes nicely without a lot of energy associated with it, and does not have some small amount of deformation there. So in this case, the door is really not effective here as we kind of go back and forth here because of this deformation at the latch. Okay, and you might say, well, what if we kind of make that, attach these two points, and then what would happen? Well, you would increase the torsional rigidity of the vehicle if the side frame is the most flexible member, and often it is. So this is a possibility. And here is a wedge door lock. This is advertised as part of the Toyota sports car here. It's basically a little wedge that's added in here. So this is the little wedge that you're seeing here, added as an aftermarket feature here, so that as you close the door, it kind of wedges into place. And that does prevent the motion that we were looking at here. Okay. And here's kind of one, this is an engineer at Toyota, and here's his quote here: "The door opening has a gap between the door and the body, like we just looked at in the previous slide. As you operate steering, there will be a delayed reaction." We talked about this when we were talking about torsion requirements. There'll be a delayed reaction as the car body is twisted. This gap here is zeroed out by putting the spacer-shaped wedge into the gap, and then clean steering results with a quick response. So we've increased the torsional rigidity, again, relative to the torsional roll rate of the suspension. We've made the structure much more stiff, and we have this improved performance. Okay, so what do you lose in this trade-off is the energy to shut the door. The door doesn't quite close as easily. You have to slam it a lot harder. So maybe with a sports car, that's a good trade-off. With a family sedan, you might be prepared to take the slightly less overall torsional rigidity of the car. Here's another way to do this. This was used by Mercedes some time ago, and basically it's like a little pin, a little wedge that goes into a hole on the body side attachment, and it does the same thing as this idea of the wedge. In this case, there's some elastomeric rubber there, so that this isn't increase the door closing rigidity. So it does have a nice compromise of increasing the torsional rigidity of the body and not having too much door closing effort. So we have to look at the other side of this as well. Is we might be able to pin that nicely, but if we have distortion at the hinge mounting points, we have to contend with that. Okay? So what does a load path look like at the hinges? Well, if we're applying a load here in this, as we twist the car, basically that's applying 4F forces at the hinge attachment points. Okay. Here's a conventional hinge that you see here. So this surface here mounts to the hinge pillar, and this surface here mounts to the door. And from the lower left corner, we see that we can have loads like this, 4F loads. So we can have this kind of a deformation here if we don't have a nice rigid hinge pillar. We can be distorting that flat surface. We know that a flat surface is not too rigid, so that's why typically we'll have some reinforcements in this area to prevent that. Here's another way to do this, and again, this is just an R&D type approach, and that's to have an element that looks like this. So this might be forged steel, or we're looking at this 4F force again, but now this element has a pin that goes all the way through to the other side of the hinge pillar. So now this force is being reacted by a force here and here, rather than by a moment being applied at the top. So this is a way to get better rigidity at the hinges, and this only becomes significant if we're trying to pin that latch area. Okay, so another hole in the side of the car that we haven't talked about is the hatch. Very similar to the behavior of the side doors. So as we twist the car, if we look at this picture here we're saying that the hatch again is this extremely rigid body, and we're holding the hinges. We have good hinge attachments, but maybe not such a good latch attachment. We'll get motion that looks like this. So one way to improve this, and you can probably guess it, is to have kind of a wedge here at the attachment point, and that would tend to make this a structural member, the hatch a structural member. Okay. Another kind of a configuration here, and again we're looking at the hatch, and here we're shearing the car, but now we're looking at the motion here along the sides, and a way that's to improve that rigidity, to make that hatch a structural member, is to add a little wedge here on the sides. And many cars have these. Often they're called anti-rattle members. And when you think about it, what's causing the rattling is because we have a too torsionally flexible a body. So it's kind of aptly named that once we put them in there, we'll increase the rigidity of the body and torsion, and the squeaks and rattles should go away. Okay. So let's just kind of summarize everything that we said here about monocoque structures here. So this is where the shell of the vehicle is a structural member. it's a relatively efficient way to react torsional stiffness. So we're just kind of going to go through what we learned so far. We talked about the source of requirements being the twisted effort for strength, being either the solid feel and the body natural frequencies, or the handling aspect where we want some multiple of the chassis stiffness. We talked a lot about this idea of the cabin monocoque as the primary structural system that reacts torsional loads. And what's important there is the shear rigidity of the members. When we flowed down the strength requirements, what we did was come up with actually a matrix formulation that was derived from free body diagrams of each of the elements, and then knowing the applied torque and the geometry of the car, we could calculate this Q vector. That's all the forces all throughout the car. Okay, and then as we're designing those elements, we could apply this analysis to it. So this was strength. And then we also flowed down the stiffness requirements, and that basically the governing equation was to balance the work being done by the external forces with the strain energy that was stored under that external force. And we use this idea that the shear flow is constant throughout this monocoque body, so we could express the strain energy with this formulation. And when we did that, we came up with our famous equation here that led us to the idea that for torsional rigidity, all the various shear resistant members that close out the monocoque add as springs in series, so that if we lose any one of them, then all of a sudden we have a very flexible structure. Okay? And each of these springs is given by this effective shear rigidity divided by the area of the panel. And the way we calculated the effective shear rigidity was with our idea of our little pinned picture frame model. We could imagine our structure being applied in here, the load being applied to it, the deflection measured, and then we can plug that in to come up with the effective shear rigidity. Okay. And then finally, the kind of insights that we got from this model, and really this is really the important area, is to have this kind of internalized understanding of how structures work. First of all, we said that this is the model for torsional rigidity. When we pull on the series of springs, what we're feeling is a torsional rigidity of the car. So if this is our model, then all the members must be present. If we take one out, we no longer have a structure. The most flexible member dominates, so if we're trying to improve a problem with torsional rigidity, what we want to try to understand is what is the most flexible of these shear resistant members, and then only work on it. So that goes on to the third point, where it's a waste of time to try to just improve all the members. We really want to get to the one that's the most flexible. And the structure's members' performance is measured by its resistance to shear deformation. So we want to kind of imagine it in this picture frame, and how stiff would it be as we applied this sideways load in the picture frame. Okay, so now this was relating to shear resistant monocoque type structures. Okay, so when the cabin of the structure, the enclosed cabin, is what's really resisting the forces. Now we're just going to take a smattering of time here to talk about torsion of non-monocoque vehicles. And what do we mean by that? Well, it's whenever we don't have the closed box. Okay, so here we're showing a convertible. So we've taken the lid off the box, and all of a sudden the box becomes very flexible, just like the shoe box that we use to kind of introduce the topic. And we understand the reason for this now is that we have these loads on the side of the panel, We can describe them as a shear flow. And once we take out a panel and that shear flow doesn't exist on this member, it can't exist on this one or this one or this one or this one. The shear flow is equivalent, and when it goes to zero for one panel that isn't there, it goes to zero for everything. So what are some ways that we can have a torsionally stiff car when we have conditions where we don't have a closed monocoque? So for example, for the convertible, we kind of took out this spring, and all of a sudden we don't have a structure unless we have something else that we put in its place. So we need some kind of a path. In this case, I'm calling it a lower load path that we would use in convertibles. So let's kind of take a look at what that might look like. There's actually several ways to do this. One is a case called differential bending. This would apply to small sporty cars. Another one is we can just have a big tube running down the car, center of the car, and we kind of we understand how to analyze tubes from what we talked about several lectures ago. We can have a slab or grillage kind of a structure. So if you're familiar with a honeycomb structure where we have an upper and lower surface, but it's spaced by some kind of a mechanism, we have a really very shear resistant slab. And then finally, we can have the good old chassis frame. Okay. And what we're going to do in this lecture is just kind of talk about each one of these in a somewhat qualitative way. We're not going to go into much detail on any of these, but just so that you're aware that there are these other methods to react torsion. So the first of these is this idea of differential bending. It's kind of an odd phrase, but you'll see why that's the case in just a minute here. And this has to be a very specific kind of a structure. So we need to have a closed-in dash. So here's a box. So this is a hollow box again. So the dash is a box. We have a similar one in the back, in the seat back. And then we have them connected by a pretty substantial rocker. Okay. And then here we're applying our twisting loads, and we'll kind of look at in a minute what is the distortion for this and why is it called differential bending. But this is really pretty limited to two-seater sporty cars. Okay? And the main reason is because we actually have this closed-in structure at the dash panel and in the back. So here is a Lotus Elise. So here's that closed-in structure for the dash in the front and in the back. Here is I think this is the same car, but now we're just looking at a different view. Some of the parts taken off. And then here's a carbon fiber car. It looks kind of conceptually very different, but here is the dash area that's kind of closed off. And here's the area in the back, closed off. Okay, so why is it important that we have these boxed-in areas? Well, we know that if you think of a shoebox, that when that shoebox is closed in and it has pretty much true flat panels, it's really, really rigid. Okay, so that's why we have these here, and that's what kind of limits the amount of space in the vehicle. So why it's limited to just a couple of people. So let's take a look at how this system works when we twist it. So we're going to apply a torque to this. Of course, there's a rocker on the other side, but we're not looking at it. But when we apply a twist to it, the thing's going to deform like this. Okay? Each one of these boxes is so rigid that it essentially doesn't distort at all. And because the rocker is attached here and here, we're basically bending the rocker beam. So even though we're twisting the car, that translates really immediately into bending the rocker. And it's kind of, if we can kind of think about this, this looks like one little cantilever beam here and another little cantilever beam here. Okay? And this is why it's called differential bending, is the main torsional resistance comes from this idea, this differential motion from the front to the back, bending the rocker. Okay. So how would you analyze this? You kind of analyze this as just essentially a rigid structure, very geometrically would translate the rotation right to the rocker, and then we would analyze the rocker as a beam and bending, and we got the tools for that earlier in the course. Here's the difficulty with this type of a structure, and here's why it's limited to usually these very tiny sports cars, and that's because at this transition area where we're applying some moment from the box to the rocker, we have some extremely high loads occurring. So that's because the torsional rigidity of the box is really high. It has to be stiff to pass this bending moment to the rocker. But this joint must be very rigid in order to do that passing along. So it's very highly stressed. Okay? So this area is very very sensitive for design. It can be done. It gives you a very torsionally rigid structure, but it can be kind of a fatigue problem unless you handle it well. Okay, so that's one way to get torsional rigidity without having a monocoque structure. Another one is tubes. So here, this is, in this case, this is a Lotus Elan. A lot of their vehicles were kind of famous for this tubular structure. So you see the tubular member here running from the front suspension towards the back here. This is a rear engine or mid-engine type car. So it has to split before it gets to the rear axle. Here's a earlier version of Corvette. So the tunnel structure is actually closed out. So the drive shaft goes through the tunnel, but there's a plate on the bottom. So this becomes a closed out member. And then the rockers are very large with a large area. So it's kind of like the sum of the areas enclosed. We know that from our little study of tubes, that the effective torsional constant that determines how rigid a tube is depends on the area enclosed divided by the perimeter. So we want to have as small a perimeter as possible in a large area enclosed. This was a very early GM electric vehicle. This was like in the early 90s. Its battery pack was actually a T-pack, but down the center of the car, there was a really large tunnel area, and there was a closeout on the bottom. So this not only held the batteries, but it also provided a lot of the torsional resistance of the car. Okay. Again, these are somewhat limited to 2, maybe 4 passengers because of the need for this really super high, large tunnel area. Okay. Number 3, this idea of a slab or a grillage. Basically, we have some kind of a core that spaces 2 faces apart. So we want to get those spaced far apart. And then this whole structure is then glued together, and it becomes a very rigid grillage. So there's a few calculation equations here to come up with a torsional rigidity for a grillage. So basically, this is just like the floor of the car would be this flat, somewhat thick, something on the order of maybe 75 to 100 millimeters tall. But that would provide the torsional rigidity of the car. The trick with this one is how do we transfer the forces from the suspension attachments to the grillage area. So that has to be handled very, very carefully. So we don't see this too much in actual use other than in race type vehicles. Okay. So the last area that I want to talk about is the idea of a real chassis frame to the car. We all know what those are. It's a member that the body sits upon, and that strong frame is generally attached to the body structure with engine or body mounts. Body mounts. So what that looks like is something like this in section. Here is where it's mounting to the body, and this will have to be a fairly substantial piece of sheet metal. Here is the frame, and here is the body mount. And the idea here is to isolate the frame from the body in two directions, in both shear and in compression. Okay? You can kind of see here that in this case we have a gap here. So here is the frame is now moving upwards here. It doesn't touch this little sleeve in the middle, so it's compressing this part of the out of the mount. It's extending this part of the mount, so it's essentially can move relative to the body structure, but there's an effective stiffness that's involved. And then the other important direction is in shear. So here now the frame is moving horizontally relative to the body because we have this gap here. We're not grounding out onto the body, so the only connection to the body structure is through the elastomeric rubber that's in it. Typically, this type of a construction is much less rigid torsionally. So here you can kind of see a range for monocoques up here. And then here's a range for cars on frames. And this is somewhat older data, so this has moved upwards a little bit, but it's still not in the region of a monocoque structure. So monocoques, the whole sole use of them is the idea that they're very effective in torsion. So let's take a look at the frame itself. There's been quite an evolution of frames. In the early days, they were actually open sections, and we know those are very, very flexible in torsion. They went through a spell of being closed, so this was welded at the time. Then in order to use space a little more effectively, the flanges went away. We got this kind of a construction until today. Many of the frames have hydroform sections, which allow us to kind of optimize the space available to us. They are often made of Taylor welded blanks, so the material properties vary along the length of the structure, and then they can vary in shape as well. So all of these went towards increasing the torsional stiffness of the frame. But even at that, the frame is relatively flexible in torsion compared to a monocoque. So now when we put the body and the frame together on mounts, we can start to get a pretty effective body structure for torsion. And we're going to kind of look at this, and again, this is just for getting some intuition into this kind of a structure. So here we're kind of looking in the front of the car, and here we're seeing the front of the frame. And it has an axis that it would like to twist around. So if we just had the frame and we were twisting it by itself, this is the chassis frame twist axis. And here is a body structure, and we're going to say for this body structure, it has all of the, all of its parts. It does form a monocoque, even though it's mounted to a frame. Okay? And here's kind of our simplified view of that monocoque. We're back to a shoebox, and it has its own twist axis. And now we're going to imagine applying a torque, probably through the suspension system, to the frame, and then kind of consider how does this system move. So here it is. Let me get rid of my little scribbles here so we can see this kind of in a more animated way. So here is the kind of rotation. If the frame wants to rotate around this axis, the structure wants to rotate about that axis. You can see that there's some shearing occurring here. Okay. And that shearing goes through the body mounts. Okay. So here is kind of the body mounts, and we're kind of showing them in the sheared position. And if we can make, it's kind of a clunky model, but here's a model of the body mount. Here's kind of the rigid part that attaches to the body. Here's the rigid part that attaches to the frame. It's got some shear stiffness, K sub X, and some compressive stiffness, K sub Y. And what we can kind of see here is that the main flexibility is going to be the shear stiffness of the mount, of the body mount, connecting the two. I've got a little animation here to show you. Basically it just takes a cutout of this front view of the body, and it forces it to rotate around a point there, and a little cutout for the frame, and it forces it to rotate through a point there, and then it has some engine mounts or body mounts here, and you'll see kind of the shearing motion. Let's play that here. So you can see that we have lots of shearing occurring. That we might have very compressively rigid mounts, but the real action is occurring in the shearing. Okay. And the more we increase the shearing stiffness, the more we couple the frame and the body, and that means we'll have a more rigid structure. Okay. So if we want to have a really good torsional rigidity in a frame vehicle, we would want to have mounts that have a very high shear rigidity. But unfortunately, we have a problem, and that's that as we want to increase the torsional stiffness and make it more rigid, that means that we're going to want to increase these stiffnesses of the mount. But on the other hand, as we increase those stiffnesses, the vibration isolation will go down. We'll hear more noises, get more high frequency vibrations when we have stiffer mounts. So we get this kind of a trade-off necessary between isolation of vibrations and noise and control of the torsional rigidity of the car. And there's no right answer. It's just like it says, it's a trade-off. We can't have both. Often the reason that we have a frame on a passenger car is because we're trying to do this. We're trying to isolate some of the objectionable noises and vibrations, so that we end up having a slightly torsionally more flexible structure. So one other item in this is that we kind of see when we're doing the shearing here between the let me get rid of some of this messiness. You can kind of see we're shearing between the frame and the body. So in the front, we're getting this kind of a shearing. If we could look in the back, we're getting shearing like this. It's equal and opposite. So if we kind of look down from the top view onto this situation, here we see now the top view, and we're looking at the chassis frame. So the frame is, if we have this nice rigid body, the frame is deforming underneath it as we apply the loads. So we can kind of see that not only does the frame have to be torsionally stiff, it also has to resist this kind of a distortion like this. We called it a diamond shape before. So it's a shearing deformation of the frame. And often the way this is done is by having really effective cross members that go from side to side. Often in many cars, if we were to look at this in this view, here's the side of the frame. These would be right through the frame rails, tubes that go all the way through. So now if we look at the top view here, the cross member would go all the way through. And what that's trying to do is to limit this shearing deformation of the frame. Okay, and this is just kind of showing you how the shear rigidity is directly related to the torsional rigidity. Okay, so this is just an aside. We're not going to go into the detail. Not responsible for this on exams or anything. But the idea is that this resisting this shearing deformation of the frame is really important. And just to kind of show you a historical example of that, here is a 1955 Chevrolet, so going way back in time. So here is the frame shape here. And there was a major change in the design, kind going from 55 to 56. And one of the things that they did was add this X member to the frame. Okay, and what did that X member do? Well, basically, it resisted this this kind of a matchboxing kind of a deformation. So that again proves that the frame has to have good rigidity to resist this kind of a shearing deformation. Okay, one last point here about the mounts, body mounts here. We've been talking about torsional rigidity in the mounts. I want to just make a comment here about vibration isolation and the mounts. So here we're going to kind of consider that the frame here has some deformation. We're saying it's a sinusoidal deformation, has some amplitude X. And this is obnoxious vibration that we don't want to have entering into the body structure. But here it's translated now into a force being applied to the body structure. So if this is at a high enough frequency, we would feel the buzzing or we would hear the noise. And we're trying to reduce that. So we can model this little interface with the mount stiffness that we had talked about before, the Kx and Ky. So the vibration deformation is occurring there at this point. We have a local mass, so this is the weight of the attachments and part of the structure. So that's the M here. And then we have a local flexibility. So this is our structure kind of deforming locally. That we talked about this a little bit. And then we have the force being applied into the body through that. So how does this kind of a vibration system behave? So this is a single degree of freedom. We have one mass, so that makes it single degree of freedom. And then we have a couple of springs in it. So here is the response of this. So this is, we're just looking at this as on a log plot for convenience. So this is the ratio of the amplitude of the force that's going into the car. We want that to be really low, to the amplitude of the obnoxious vibration occurring on the frame. Okay, so we want this to be small to isolate vibration. Okay, so over in this region, we're isolating the noise from the car because we have this flexible mounting stiffness. If we lower it, we isolate even more. Okay, so that's the good thing. So this kind of goes back to this idea that for torsional stiffness, we want the Kx and Ky to be large to couple the torsion of the body with the torsion of the frame. But for this idea of vibration isolation, this is why we want the Ks to be small. Okay, so we're just kind of stuck with kind of finding the best balance between the two. Okay, so this really rounds out the topic of torsion. We talked about monocoque cases. We talked about briefly about structures that are non-monocoque. So what we're going to do next time is really kind of change directions, and we're going to start to talk about crashworthiness. And the first load case that we're going to be looking at is front crashworthiness, the full frontal barrier impact, and we're going to try to come up with some simple first-order models that will allow us to understand what does our body structure need to do to protect the occupants in that impact. Okay, so we'll see you next time.